All right. Hello, everyone. Welcome to our last seminar before the summer break of this series on tipping dynamics in social and natural systems. We're very happy to have Kwakkel here, who was originally planned to give a tutorial for us. That didn't work out, but now we're very happy that you can still participate by giving a talk. So you're a full professor at the TU Delft on decision making under deep uncertainty, and so I think the topic today will also focus very much on uncertainty when we model tipping dynamics. So please go ahead.
So thank you. So I'm Kwakkel. I'm a full professor at Delft. And I've given a talk quite a few years ago more about how to bring complexity science ideas into the policy arena. Today I'm doing actually something a little bit the other way around, drawing on methods and techniques from quantitative policy analysis to investigate tipping points, tipping dynamics. And I'll have a more socioeconomic example to illustrate some of these ideas. But by and large, a lot of what I do is sort of on the intersection of political decision making and how to bring information and knowledge into that. But I work very hard to work on the modeling side. So I do a lot of agent-based modeling using differential equations, that kind of stuff, and then use that to inform public deliberation and decision making. And so you already speak of tipping dynamics, and that is, I'm very happy to hear that, because the word tipping point always makes me very, very nervous. The Austrian philosopher Ludwig Wittgenstein remarked at some point that image holds a skeptic. And with that, he meant that a certain way of phrasing something can really strongly affect what we see. And there's a simple example, a simple illusion there, which is known as the duck-rabbit illusion. And if you look at it, if it's called duck, you see a duck. If you call it a rabbit, you see a rabbit. And it's virtually impossible to see the duck and the rabbit at the same time. And I have a sort of similar issue with the word tipping point, in that in general, it's not a single point. Particularly what I'm interested in, where I'm interested in uncertainty. Tipping is a function of a whole bunch of uncertainty. So it's some kind of hypersurface where the system shifts from one kind of state to another state. In general, this surface is not a clear, clean boundary, but it's fuzzy. And it's also not always self-evident what the states are between which a system is said to be tipping. Sometimes, for example, in ecological systems where we have a rainforest or a tundra or a savanna, there are clear, distinct states. But in a lot of more socioeconomic work, it's not evident upfront what the states are we're interested in between which this system is tipping. And that means there's a strong component of choice by the analyst when we start talking about investigating tipping dynamics. And in fact, depending on how you define your state, it might change whether you see clear boundaries or not. And then another issue is the proliferation of the concept. So we have Earth system tipping points. I've done a lot of work in the past with Marjolein Haatsnoot on adaptation tipping points. And so adaptation tipping points are basically the conditions under which a change in policy is needed by a government to prevent, say, a coastal city from experiencing too much flood. We also have increasing talk about positive tipping points. We have socioeconomic tipping points, and without a doubt, if I spend a quick literature review on this, you can find 100 different notions. I want to give trigger point at each day in the context of polarization literature, for example. So that being said, what do I mean when I talk about tipping points or tipping dynamics and their identification? The metaphor I like to use is this phase diagram idea, where I try to understand the various states, and we'll get to that, what that can mean in a minute, that a system can exhibit. And then I try to identify where in the uncertain model input space the system shifts from one state to the next. And everything I said before still applies. So these transitions might not be clean cut, and they're typically not a single point, but they're typically hypersurfaces in an n-dimensional space. Then, of course, what do we mean with phase? And this simple example with water, it's sort of quite obvious what the states are that we're talking about. But in a lot of my work, where I'm looking at socioeconomic systems, I'm not looking at a single state, but I'm looking at typically the dynamics over time, and I'm looking at qualitatively different dynamics that a system can exhibit. And so to take an example, imagine that you have a simulation model of a pandemic outbreak. We have dynamics where we have a very, very rapid outbreak resulting in a lot of casualties. We can have sort of oscillating dynamics where we have periodic outbreaks, or we can have dynamics where the disease barely takes off. And these are qualitatively different temporal dynamics. That's a temporal way of looking at it. You can do the same in space. So an example I'll show at the end is about coastal retreat. And although there in my own work I focus on the temporal dynamics of this coastal city under flooding, you can also look at land use patterns and see qualitative changes in the land use patterns, and that can be a more spatial way. And then of course you can also look at that in a spatial temporal way, where you look at the spatial change over time. The other thing is that this is all still more or less a single outcome, so casualties in case of a pandemic. An open question still is how we look at this if you have multiple outcomes of interest simultaneously. And this is particularly relevant in sort of a decision-making context where various parties to a decision have to negotiate. And taking the pandemic example, on the one hand, we care about how many people die from, say, a COVID outbreak. At the same time, there's also how socially disruptive the outbreak or your measures are. There's also the economic consequences. These are all different outcomes and they're all relevant. And I think there's a need to start thinking more systematically about the co-occurrence of certain types of outcomes, rather than sort of separating them out or exclusively focusing on only one of them. For those that are following the interviews in Parliament in the context of COVID, this is very much one of the sort of latent issues that's being put forward by various people, which I find quite interesting from my perspective as someone working on that interface. Okay, so then one step more, I'm interested in the ex ante, so the upfront identification of tipping points. And that is because typically I work on advising governments or other typically public actors on how to prepare for certain changes. So here we have the Port of Rotterdam, and we see a massive petrochemical cluster. We see some kind of logistics, there's some flood defense measures here. And I've done a lot of work in the past with Port of Rotterdam to look at its competitive position. And there we look at developments for the coming 20, 30 years. And so if there are tipping dynamics in the competitive position of the Port of Rotterdam, say in the global container network, ideally we would like to know that upfront. But this automatically means that I have to rely on simulation models. And I use these simulation models to create data, and then we analyze the data coming out of the simulation models. And this is quite different, I would argue, from those that are looking at historic data and trying to find evidence of tipping points in that. And I think actually doing it with model-based results is a lot easier because you have full control, you can always create more data. At the same time, what you might find in your models might not hold in the real world. So like I said, I'm interested typically in the use of models. Anyone knows what this picture is taken, by the way? So this is actually quite a fun place. This is het waterloopkundig bos these days in the province of Flevoland. It's now onderdeel van Staatsbosbeheer. But here you have a lot of physical models of the hydraulic structures that were built for the delta floods. And a lot of pensioned engineers are now slowly restoring all these models, these physical models. But it's also become a major reserve for all kinds of rare semi-aquatic species, animals, but also plants. And it's a very, very nice place to be. And to just see these physical models. But this is what I do, but then typically with computer models. And what of course is nice with these computer models is that we can easily change our assumptions, change our forcing conditions, and create a lot of data. And this is sort of the link to the uncertainty side of things. And because a critical point made 30 years already by Steve Bankus was that when we have insufficient knowledge, or whether there are unresolvable uncertainties that preclude building the circuits for the target system, models must make guesses at the details and the mechanisms. And any such a combination of guesses constitutes a model. And that provides a computational experiment that reveals how the world would behave if those various guesses were correct. And when I say that uncertainties are unresolvable, this means several things. And so in a lot of cases, when you're dealing with public policy problems, there's profound disagreement between the various parties that are involved. And any attempt to reduce the uncertainty to, say, a probability density function will be contested by parties that don't like that, and therefore can become a barrier to decision making. In fact, if you don't like a report in public domain, the easiest way to undermine the report is to foster your own report with slightly different assumptions, resulting in a different conclusion. And this means that in particular in a public context, thinking we can reduce all our uncertainty or characterize all our uncertainty perfectly is often actually a recipe for problems, rather than that it creates a space in which decision making can proceed. Okay, another thing that we can often do is that we impose what is in our literature called the exploratory framework or the system diagram. The people with a control systems engineering background will recognize this style of diagram as well. We have some kind of system. There's a bunch of external forces acting on that system. There's a bunch of knobs or policy levers that we can turn, and out of this comes the outcomes of this system as a function of these external factors and these policy levers or these knobs that we're turning. And this means that when we have a simulation model of these relationships, we can start thinking of running the simulation model just as a function. And so we can just map alternative realizations of the uncertainties, alternative choices for the levers into map those to outcomes. And we can do this repeatedly. So we can do this thousands upon thousands, millions upon millions of times. So basically what we're doing is a form of ensemble modeling, but in this work, we typically explicitly include also structural uncertainty. So that might mean that we have alternative functional relations between parameter A and parameter B. There might be different theories or different beliefs by the different parties involved about this relationship. And rather than heroically assume one of them to be right and the rest to be wrong, we will include those alternative assumptions and we'll see to what extent it makes a difference for the outcomes in the end. Our uncertainties are also more than just the initial conditions. And so they can also be, for example, if you have a pandemic model, yes, we have the initial conditions for how many people are sick. There's also a lot of uncertainty about how infectious the disease is, how the contact rate will change. And these are not initial conditions, but these are the parameters that drive the system. So we're looking at more than just initial conditions when we do this ensemble modeling. There are sort of three arguments why in this sort of exploratory modeling world we use ensemble modeling. And so there is the argument from uncertainty, which is the argument I've been using so far. And that is that we have partial and incomplete knowledge of the target system and its parameterization. So rather than take a heroic guess, we try to encompass more comprehensively the guesses we could be making to figure out which guesses make a difference and which ones don't make a difference. There's also a more complexity argument developed quite extensively by Scott Page and the model thinker. But the basic idea there is that real-world systems are multifaceted and there is no single best model to characterize these systems. And there are some nice examples that I know of in biology where we have two different theories that are, from an empirical point of view, equally good in explaining the phenomenon. And there is no way of choosing between these different theories. And so we end up having to use them both. And then there's the more sort of policy sciences argument, namely that there are many rival ways of understanding what the system even is and what the system boundaries are. They'll differ. How the system itself internally works. Often there can be stakeholder-specific local knowledge, for example, that isn't in line with theoretical knowledge. The worst you can do is ignore the local knowledge. So that's another argument for this ensemble modeling approach. Okay, so what then does this entail? And so the basic idea is that we create an ensemble of computational experiments. We evaluate that, we fill up a database with model results, and then we have to make sense of it. And broadly speaking, there are three families of techniques that we use to search through this space of possible experiments. So there's some global sensitivity analysis work, or basically how much variability over that in an outcome of interest is due to variability in different input parameter that we have. Another question is more, can we partition the model input space, and so the space of possible assumptions we could be making, into regions with qualitatively distinct outcomes? And so this is very close to the space diagram idea that I showed you earlier. And then the third one, which I won't discuss in great detail, is the use of many objective, typically evolutionary algorithms to search through the space in a very targeted way. For example, given all the uncertainty that we have here, what is the worst possible outcome that we can get? What is the best possible outcome that we can get? Can we find in the model input space where the system shifts from one dynamic to another? We can also formulate that as an optimization problem. But like I said, I'll leave that out for the remainder. Okay, so what does that look like in practice? And here I have a very simple example of a pandemic model. This is actually work we did 14 years ago on the Mexican flu. And so imagine that we have a simple simulation model where we have two regions, the global west and the global south, that have their own seasonality, and there is some traffic between those two regions. And then you can get a dynamic of how this Mexican flu can evolve over time. And I'm looking at the casualties here in region 1. And what you see here is one possible dynamic depending on a parameterization of this model. And what we see here is the casualties going up sort of in 2 steps, reflecting the seasonality of the disease. So this is one possible way in which the Mexican flu could have played out. That's not so useful, so we can look at it more. And so here we have 3 different dynamics, and one where basically nothing happens, and one where there's still a bit of seasonality, but it's more like it's going upwards and then it flattens out. And so, okay, we already know more. We start to get a sense of the kind of dynamics that this system can exhibit. But 3 is, of course, clearly not enough, so let's look at 100 realizations. And so here I have 100 different samples over the infection rate, the contact rate, and some of the other uncertain parameters in this model, and I get an ensemble of possible results. Okay, fine. Now what? And we know a lot can happen, how we can have realizations where there's no real reason to be concerned about, and we have realizations where many, many people die. So we haven't learned much so far. So what we now have to do is analyze this ensemble and see if we can extract information from it. And one thing we can do is to say, okay, let's try and look at those dynamics in the model output space and see if we can identify qualitatively different temporal dynamics here. And one way we can do that is to use time series clustering, so I've done that here. So I ran a time series clustering algorithm on this data set, and due to the overplotting in this example, you only see 2 of the clusters, but there are actually 5 qualitatively different clusters here. And then on the left-hand side, you see where in the parameter space these different results come from. So now, of course, this is still not that useful, but we've gone from, in this case, 2,000 runs back to 5 qualitatively different dynamics. But on the left-hand side, it's still difficult to figure out where each of these clusters comes from. And so what we then can do is use rule induction algorithms on the left-hand side to see if we can find simple rules that help us identify regions in that model input space that have a high concentration of runs of a specific cluster. So what does that look like? Now here I've taken one of the clusters. This is the cluster where we have the more sort of serious outbreak. And we see, in this case visually already, that most of those orange dots reside in the upper right corner. And of course, this is 2D, so we can do it visually. If this is 5, 7, 10, 20 dimensional, we need something else to help us come to grips with this. So one thing you can do is use something like a classification and regression tree, or in this case, a patient rule induction method, which is a slightly different rule induction algorithm, to find a box in this case that contains as many of the orange dots and as few of the blue dots as possible. And what this basically tells us is that if the contact rate is above some threshold and my infection rate is above some threshold, there's a higher propensity of getting a bad outbreak. But of course, you can also see we don't have perfect separability here because there's still a lot of blue. So you could also say, let's make the box a little bit smaller and go, for example, to this corner or even smaller. But these rule induction algorithms help you balance the quality, basically, the precision and recall of this kind of stuff. Here I'm using a very simple approach because I want my rules to be interpretable. And the nice thing with this rule set is that it's just a conjunction of if this threshold on that parameter and that threshold on that parameter, then I get into trouble. And if you're dealing with 5, 7, 8 dimensions, those rule sets are relatively easy to interpret. But of course, in this case, you might want to do some kind of logic model with a diagonal. Problem with here it still is possible because you can basically say alpha contact rate plus beta infection rate higher than some threshold, we have a problem. But try doing this in 5, 7, 9 dimensions, it becomes much more difficult. So in most of our work, we stick with these rules. And there's still some pre-processing tricks you can do to simplify this. But unless you're dealing with very nasty models, this works reasonably well, actually. And sometimes we go to slightly more supplements. Here I give you another example. Here I just picked a different cluster. And this one, there's still clearly a relationship. And if the infection rate is higher, we get more of these sort of lower things. But to what extent there's a clear pattern on the contact rate, we can't really see. And so this is a much messier case, basically, to make sense of. So that's the other thing that you have to bear in mind when you're doing this kind of stuff. Okay, that was sort of conceptually the idea. Let's now do this for an actual case. And the case study that I'm using here is of a coastal economy exposed to floods. And it's heavily based on a thesis of an old student of mine who actually now works at PBL, doing some of this kind of stuff with image. Okay, so what we're looking at is a evolutionary climate economy regional agent-based model. And so think of a city like New Orleans. So it's a coastal city. It's a coastal city that's exposed to flooding. It's a highly simplified model. It's been developed by the group of Tatjana Filatova. And here I cite one of her PhD students because that's the version of the model that we used. And what we have in this agent-based model is we have households and firms. Firms work in one of 3 sectors: capital goods, consumables, and services. And the households work in one of these 3 industries. They earn an income and they use that income to consume goods, buy capital goods, and consume services. Depending on wage dynamics, households might shift jobs, and likewise, companies, if they think they can make a profit, will enter the market. But if they fail to make a profit, they'll go bankrupt and they'll leave the model. The next step is then that you introduce a flood event, and we want to see how basically the economy responds. Because this is a partially open system, people can also leave the city if the job prospects are bad, or if the job prospects are very good, people will migrate into the city. And itself, it's a Keynes-Schumpeter evolutionary economic model, building on the work of Dorsey, who has built a lot of these agent-based models over the last 20 years or so. This is a climate-specific version of that model. And I'm looking at a single region. We also have in the group of Tatjana a 2-region model, and we're doing some of this same kind of analysis with that now to see what's going on. Okay, a more detailed breakdown of what we have. Just the diagram of the model itself. Like I said, we have firms in one of 3 sectors. Firms make investments. So they buy machines from the capital goods sector, and then they produce services for the consumption sector. They buy machines to produce consumption goods, and there is learning happening as well. Then we have the households. Households contribute labor to the firms and receive a wage or an income in return, and they buy goods and services. The households receive subsidies from a government, and the government taxes the households, and the government also taxes the firms. And then both the households and the firms can make adaptation decisions. And so they can decide to invest some of their income in flood proofing, for example, in various ways. And then with the rest of the world, there's trade and migration. And this is then more of a breakdown of the internal logic of the agent. And in this particular model, we can also sample over alternative rationalities for the agent. And so we can have a sort of rational choice utility model or a more prospect theory based way of modeling the agent. Although we didn't explore all of that for this particular study, but we can do this for structural uncertainty in. Okay, what kind of dynamics can this model show? Here we see two possible realizations. So this is just a default parameterization of the model. 2000 stochastic realizations of a single parameterization of the model, so it's a highly stochastic model. And colored here is the lowest 10% of the data. Unfortunately, I didn't have a version of these plots with the scaling on this axis the same. But basically, what we see is that qualitatively, whether there's a flood or not doesn't really seem to matter a lot because the patterns of the dynamics are roughly the same. What we do see, however, is that in case of a flood, there are more sort of cases where the population collapses and then slowly starts to recover, with some exceptions. And here the population tends to grow a little bit more, although even there can be an endogenous decline, irrespective of what the flood is doing. So the economic system itself, there's business cycles here, so that can also result in endogenous collapse of the economy, basically.
What's causing then the decline of population?
Basically, because of the business cycle, certain businesses with all the technology go bankrupt. Therefore, there is a lot of unemployment, and then people decide that there are better prospects elsewhere, so they migrate from the city away, and that causes the collapse of the population. Yeah. So then the experimental setup. So in this particular case, we looked at 8 uncertain parameters. So some of those are really about the behavior of the firm. For example, the amount of debt the firm can take on as a proportion of the total sales. We can look at how sensitive the wages are to the productivity of the firms, and therefore how sensitive wages are with a small delay to technological change. There's a markup. So basically, how do firms translate costs into prices for their goods and services? The capital output ratio. So that's the size of the capital stock a firm requires in order to produce output. There's some thresholds related to immigration and emigration. There's a discount rate, and then we play around with the timing of the flood. Because when we did the study, the question we were interested in was, okay, to what extent does it matter when the flood happened? And can we collapse the system by a single flood or not? So what we did, we had a single fixed flood, and all we did was play around with the timing of that single flood across and how it interacts with all the other parameters. We did 2,000 experiments for this using that hypercube sampling, and then we ran 40 replications for each of these experiments. 40 replications was on the low end, but due to computational constraints, this was the best we could do. And then we tracked the household population, the GDP, the median wage, and the Gini coefficient.
So how does stochastics come in here?
Okay, so
probabilities between certain.
So this is an agent-based model.
Yeah.
So first of all, the order in which agents act is stochastic, because you cannot represent true parallelism. So one day this household might apply for a job first. The next realization, I might apply first for a job, and therefore you get different kind of dynamics. There's a little bit of stochastics in technological change, for example. There's some stochastics in some of the other equations as well, and those are characterized more by probability density functions, all of which is based on actual real-world empirical data gathered actually in, I think this particular model was using some US data, so household data, household market data, and some firm data. Okay, so what we then first did was just get a sense of the sensitivities of this model over time. So here you see the 4 different outcomes of interest, and then you see over time how much of the model variability is driven by each of the different uncertain parameters. And for those that want to know, I actually didn't use something like Sobel because computationally that would be prohibitive to do, but I used X-Tree's feature scoring technique, which from earlier work we know correlates very well with global Sobel total order index. And what you basically see is that these two outcomes are primarily driven by this initial markup, whereas these two outcomes, it starts with the initial markup, then, not surprisingly, the timing of the flood starts to enter into it, but the longer term dynamics are primarily driven by the weight sensitivity to productivity. And so we see already here that there's a time varying sensitivity for at least some of the outcomes. The other question then, because I look at total influence, I don't look at interaction effects. And since we're interested in floods, the next question is to what extent is there an interaction with floods? So we can do the same analysis for the model that we ran of the exact same experiments, but with the flood set to 0, so no flood happening. And then you get this. And if you go back and forth, there is basically the same pattern. And so there doesn't seem to be a high interaction between the timing of the flood uncertainty and the other sensitivities. So yes, it does matter. The timing of the flood does matter for the final outcomes, but in terms of how sensitive the model to it is, it does matter a lot. Okay, then next question is, okay, what are the states of this simulated system? So we again use time series clustering here, and we settled in the end on 6 qualitatively different dynamics. So sort of the technical details, we use what's known as a complex invariant distance metric. So it's basically a Euclidean distance metric with a penalty term for how wiggly a line is. And from earlier work, we know that it works actually quite well when you want to do time series clustering. Then we use the hierarchical clustering algorithm and a knee criterion to settle on the number of clusters. And here we see 6, what we would argue, qualitatively different dynamics. And so we have a sort of slope, a bit of a decline, then it goes up. Here it sort of settles in sort of a middle thing, but it doesn't really recover, at least not on the runtime we're looking at. Here we see a clear sort of collapse dynamic. Here it's similar to this one, but even more quickly goes up. And here we have a decline with a bit of a growth and with less growth. And so qualitatively, you could argue that these are qualitatively different dynamics. And next, for each of these 6 clusters, we asked, okay, from where in the parameter space did these results originate? So we ran this patient rule induction method on that, and then you get this table. And so we see basically that these two and the full growth, full level off, are a combination of initial markup and capacity output ratio. The growth collapse is the initial markup in combination with minimum unemployment and flood timing. Steady growth is again for the first 2 uncertainties, and then the last 2 are primarily driven by just the initial markup. And so we've gone from 8 uncertainties to basically identifying 4 that matter, and 2 of those only matter for one very specific dynamic. They don't matter for the other dynamics. Now that we know that it is mainly driven by just 2 parametric uncertainties that we're looking at, we can visualize it actually in a similar way to a phase diagram, and then you get something like this. And so here you see where each of the different dynamics originates in the input space over which we were sampling. And what you basically see from a distance, there's a surface, there's a bit of a triangle here, another triangle here, a bit of a red corner triangling here with the blue around it, and then a purplish band, and then we have the brownish band. And so we clearly see how, in this case, much more clearly than my pandemic model, different kind of dynamics originate from different parts of the parameter space, but there are still slightly fuzzy boundaries between them. So we can actually visualize this using the rule induction algorithm, and then you would get something like this. And where we try to find rules that capture that region. These are just parameter spaces I had in the 2 slides ago on the table, but here were visualized, and we allow a bit of efficient boundary because how we balance precision and recall in the algorithm. And what we learned from this is that the collapse dynamic, which is the brown one, is almost exclusively driven by the initial markup. So if the initial markup is higher than 0.3, we'll get a collapse dynamic no matter what. We also see that if there's a substantial overlap between the full growth and steady growth dynamic, and so that cannot be explained by these 2 parameters. We need that other parameter pair to start differentiating between those 2. And we also see here that the capital output ratio primarily differentiates between primarily relevant for one had a fall and then stabilizing dynamic or the steady growth dynamic with a little bit of interaction to the initial markup. But here we have in essence a phase diagram style visualization of the kinds of dynamics that this system can exhibit. But of course, there's all kinds of follow-up questions that we can do because this master thesis work was very much a proof of concept study, but I think interesting results nonetheless. So let me wrap up. While you are already starting with tipping dynamics, and I agree, I think it would be nice to get rid of the term tipping point as such. I don't like the term at all. I think it confuses rather than clarifies. I also think that sort of this phase diagram analogy, at least for the kind of work I do, is useful, and that we can find those diagrams, create those diagrams using large-scale computational experimentation with rule induction and ways of defining the states, as I did it here with clusters. The stochastic realizations are sort of glossed over, but that's a problem. If you remember the 2 plots with the floods and no floods in purple, you see a lot of variability even within a single experiment. And what we did here, just for the clustering itself, we took the average over the stochastic realizations within a single experiment. And a better way to go is probably to look at do the clustering over the full dimensionality. So basically all your experiments and all your realizations. But then in this case, we would have 18,000 time series on which to do the clustering. And you can parallelize the clustering calculation, but it's annoying. So it's solvable, but not by this master student in the time we had available. And then you can look more nuancedly at within a given experiment, how many of the stochastic realizations show a collapse dynamic, how many show steady growth dynamic, and you can start doing the analysis in that space. And that might be more revealing still than what we did here. And then a third question of issue is that I relied heavily here on being able to produce human interpretable rules. With the idea that in particular, if you're doing high dimensional spaces, that might work. But there are all kinds of other techniques that would allow us to give a low dimensional projection of that high dimensional data with cleaner separability. But then you sacrifice human interpretability of the rules. So again, to be discussed, or at least I don't know what the answer is there. Thank you.
Thank you very much, Jan.